Hello, students. So today we are going to do the next question of chromatography, topical past papers of A2. So let's start. The dipeptide phenylalanine tyrosine has the following structure. So this is the structure of this dipeptide, and this is the electrophoresis. It is subjected to electrophoresis. So a dipeptide and its two constituents, obviously. In the buffer at pH 12, at the end of the experiment, of the following results were seen. So now you have to focus over this point of pH 12. This is a basic pH, obviously. So what will happen in this basic pH? Obviously, if I talk about this dipeptide, so this will lose this proton, and obviously, this part also lost proton. So overall, it will have a negative 2 charge over it, because if I just remove this hydrogen, if I just remove this hydrogen from here, and if I just remove this hydrogen from here, because obviously in basic pH they will lose their proton, and it will have a negative charge over here and a negative charge over here. So this species has overall charge of negative 2. Okay, now if I just talk about, okay, one thing more, that if you just look at the data booklet, so this is the phenylalanine structure and this is the structure of tyrosine. So you can just identify that this portion was for tyrosine, and this portion was for phenylalanine. Okay, so if I just talk separately about the phenylalanine, so it will be like this one, and then this is like CH, and this is NH2, and this is COOH. Okay, because obviously we had three constituents. This is a dipeptide over here, and the two, tyrosine and phenylalanine. And if this is phenylalanine, and if I just draw a tyrosine over here, so it is having another OH group over here. The structure is just similar. You can see that this is OH present over it. Now, if you just provide the basic pH, obviously over here also. So here you can see that in the presence of OH negative, for example, in the presence of basic pH, also this will lose. So this will lose its one proton, obviously, of this COOH. So after losing this proton, this will be COO negative in the basic pH, and this will again COO negative. One second. This will be COO negative over here, and this will also lose this of proton, so it will have a double charge over it. It will be O negative over here. So these are the three, you can say, our ions, for example. So obviously these are negatively charged. So because these are negatively charged, so therefore they're attracted toward the positive plate. Okay, so they're attracted toward the positive plate. Now we have to see their movements. Their movement, their rate of movement, it depends upon two things. One is their MR, second thing is their charge. Okay, the greater the charge is, the greater is their movement. The lighter the mass is, the greater is their movement. These are the two things that are very important actually. Now, obviously, we have to tell that which species is responsible for the spot P. Okay, so what do you think that as you can see, tyrosine has a negative 2 charge overall, and if we just talk about the phenylalanine, it is a negative 1 charge in basic pH, and it also has a negative 2 charge. But because it is a dipeptide, and its molecular weight will be greater, obviously, so therefore it will not as much faster. And in the similar way, if we just compare this and this, so this is having a negative 2 charge. So obviously, it will move much faster, because the charge density, if it is greater, then it will move faster, obviously. And your basically molecular mass ratio is not as much, like there is not as much difference. So that's why. So the P will be obviously tyrosine. P is a tyrosine. The species that is responsible for the spot P is actually a tyrosine. Okay, and why it is tyrosine? Because it has a tyrosine has negative 2 charge, and it has smaller MR as compared to a dipeptide, smaller MR. Okay. Now, the next question. Suggest why other two species give the spot oranges are so close together. Now, you can see this is a dipeptide. As you can see, this is a dipeptide. It's a greater, it's a MR is almost double than that of phenylalanine. As you can see over here, its molecular mass is almost double than that of phenylalanine. Then why their spots are just close together? You can see the two things. I told you that the rate of movement depends upon two factors. One is actually its MR, and second is the charge. So it's actually directly proportional to charge and it's inversely proportional to MR actually. But you can see their charge to mass ratio or mass to charge ratio, anything that you are taking which ratio, that's actually similar for both. Why? Because its charge is double than that of phenylalanine. While obviously, so its charge is double, and while MR of this dipeptide is doubled. Okay, so because you can say that their mass to charge ratios are about the same for each of these two compounds. So therefore, you can say that they will just give the similar, the similar, spot position. They have the spots. Okay, so their spots are very close together, and the reason is actually their mass to charge ratios are about the same for each. Okay, because negative 2 charge of dipeptide is about double than the charge of the phenylalanine, but the MR is also, you can say, double. So that's why. Uh, Due to charge, it should move faster, but due to molecular weight, it should move slowly. So that's why it's like same. So I'm just writing the answer over here. It's like obviously mass to charge ratio are about the same for each. Okay, mass to charge ratio are about the same for each. For each dipeptide and phenylalanine. Okay, so this is the answer. Now, this is the question of 2017. Now, another question for 2017 is like a mixture of the three different compounds, G, K, and L. And they were analyzed by thin layer chromatography using a polar stationary phase and a non-polar mobile phase. And the three compounds all have the similar molecular masses, and the resulting chromatogram is shown over here. So you have to focus upon the what is the stationary phase, what is the mobile phase. You can see the stationary phase is a polar, as you can see over here, while the mobile phase is non-polar. Okay, and they have almost similar molecular masses are similar, obviously. So, you know that in thin layer chromatography, the rate of movement depends upon the polarity of the mobile phase plus polarity of the stationary phase. Now, if the mobile phase is non-polar and if a compound is polar, so polar compound will have more attractions for polar stationary phase. For polar stationary phase. While non-polar compounds will have more attractions for non-polar mobile phase. It means that the compounds that are non-polar, they will move much faster in the non-polar mobile phase, and polar compounds will remain with the stationary phase more, and they will show least movement. Now we will check out that which spot is for which compound. Now spot one is actually will be for the most non-polar compound because it has moved most with that of the non-polar mobile phase. So that's the reason that our the you can see over here, as if I just draw it like this, CH3, C double bond O, okay, then C double bond O, OH. Okay, so it means it's a carboxylic, and you know carboxylic acid is a polar compound. Okay, now another, this is C double bond O, and this is a dioic acid, no? Dioic acid, a double carboxylic acid group. And the third one is actually simply a ketone, Ca3CH2, C double bond O, although it's a polar bond, but as not as much as that of the carboxylic acid. So it means the most non-polar out of these three compounds is actually, you can say L. So therefore, L will show 1. Okay. Now, out of these two compounds, obviously dioic acid will be most more polar out of this, because this containing the two carboxylic, the two dioic acid groups. So that's why the most polar is like 3. So 3 will be for dioic acid, and the remaining 2 will be for J. Okay, so this will be so. Now, I have to explain my answer to B, obviously. So, the more polar the compound and the stronger attractive forces to the polar stationary phase. Okay, so that's the reason. So, I'm writing the answer. The more polar the compound is, and the stronger attractive forces to the polar stationary phase. The stronger attractive forces to polar stationary phase. Polar stationary phase. And what is meant by, okay, and you can also write the answer with reference to the non-polar compound, like the less polar compound is the weaker attractive forces to the polar stationary phase, and that's why it will move faster. So you can write any, because it's a 1 mark question, so you can write with reference to only one. Okay. So what's RF actually? RF is the distance moved by the compound from baseline over distance traveled by solvent fluid. Okay. So this is actually the question number 8 of the 2017 paper.